Okay, so today we start from the balance. So last week we have already seen that in order to describe a plasma, we need to know the parameters of plasma. So the parameters including the electron temperature, electron density. These two are the basic properties of plasma. But also we need to know the degree of ionization and electron temperature distribution function. Okay, especially if the plasma is not a thermal plasma. If the plasma is generated by electrical field, then we have to know the electron energy distribution function. Okay, and we also see the figures with a vertical axis of the plasma density and the horizontal axis of the electron temperature. So in that figures, we can also find out a parameter, the Debye length, lambda sub d. Okay, so the Debye length is a scale. If we look at the plasma at larger scale, larger than few Debye lengths, then the plasma can be considered as an equipotential state. Equipotential. So it means the potential inside the plasma is a constant value. The potential distribution is uniform in the plasma. If we look at a scale larger than few Debye lengths, okay. But if we look at a very small scale, very small scale, we can find out that actually there is a disturbance of potential. If there is a charge, negative charge, electrons or positive ions, right? So close to the electron or the ions in this very small region, we can find out the potential in the space is distributed like this way. If this is an electron, right? So the electron compared to the uniform plasma potential, this place will build up a negative potential profile. So with this negative potential, if one electron travel close to this electron, the electron will experience a repelled field. But if a positive ion traveling close to this electron, the positive ion can feel the attractive force by the electrical field. So in other words, these electrons can attract ions or repel another electrons. Right? So the individual electrons will affect the traveling of the charged particles. If we look at a scale smaller than the Debye length. But since there are many electrons and ions in a plasma state, so there are many potential disturbance in a very small scale. But in average, okay, the field generated by the individual charged particles are shielded. Okay, if the distance is long enough. So if the electrons or ions travel far away from this individual negative charge, or individual positive charge. So they will not be attracted or repelled by this individual positive charge or negative charge. Okay, so in that case, those electrons and ions are considered freely. So they are free electrons inside the plasma, and the ions also can travel freely without being attracted by this individual electron. So actually, there are two scales when we study the plasma. If the scale is smaller than the dipole length, then those charged particles will attract or repel each other. But if the scale is large enough, we can consider the electrons and ions can travel freely without being attracted by individual charged particles. Okay, and okay, yeah. So this page describes this phenomena. Okay, so if the scale we are looking at is much larger than the dipole length, much larger than the dipole length, then all these charged particles can move freely. And when we study the phenomena of plasma, we can study the collective phenomena. So in this part, the second part of the nature of plasma, I will go through three collective phenomena. So one is the plasma shift and bipolar diffusion and the oscillation of plasma frequency. Okay. So if the scale is larger enough, so the D is the scale or the dimension of our plasma system is much larger than the dipole length, we can just look at the collective phenomena of plasma. Okay. So the size must be larger than 1 or 2 dipole lengths. Okay. But if the size is smaller than 1 or 2 dipole lengths, or those particles will interact. So the interaction of the individual of the charged particles. Okay. If the length is larger than 1 or 2 dipole lengths, the interaction is not important, so they become immaterial. But if the length scale is smaller than 1 or 2 dipole lengths, the charged particles start attract each other or repel each other. Okay. So if we study plasma in a large scale, we can just focus on their collective behavior. And let's come back to the previous slide. Okay. So the potential distribution or instantaneous potential disturbance by a charged particle, right, can be described by this equation, delta V of x. Okay, so here this horizontal line shows the average plasma potential. Vp, P is plasma, so V sub P is the plasma potential in a plasma system. So this is the average plasma potential. So if here is an electron, okay, the electron is negative charge. So in this space, the potential distribution will look like this way. So at the center of the electron, the potential is a negative value, right? Compare with the average plasma potential. And the potential difference between the plasma potential and the local, the potential at the local space is delta Vx, delta V of x. So delta V of x equals delta V0 times exponential minus x or divided by lambda d. So the potential difference will change with the distance from the center of the electron or center of an individual charged particle. Okay, and if you analyze this equation, you can get lambda d, right? Lambda d in this equation equals to kTe epsilon 0 divided by NE squared, and the square of the square root of this part. Okay, so in this equation, K is the Boltzmann constant. Boltzmann constant. Epsilon 0 is the vacuum permittivity. Vacuum permittivity. Okay, and E is charge of one electron. So these three parameters are constant. They are constant. So in this equation, you can find out the lambda d, the balance depends on the temperature of electron and density of electron. Density of electron. So when the density of electron is high, then the lambda d is small. Lambda d is small. And the other thing is about the temperature. So if the electron temperature is high, then lambda d is long. Okay, so lambda d depends on the electron temperature and electron density. Electron density. So in previous let's see. Yeah. Okay. So in these figures, right, we can distinguish plasmas by their electron density and the electron temperature. And in this figure here, the horizontal lines shows the balance of the plasma system. The balance of plasma system. Okay, so so the balance depends on the electron temperature and electron density. Electron density. So if there are a lot of electrons in your plasma system, a lot of electrons. So those electrons will shield the potential field from other electrons. Shield the potential field. Okay. So that the effective balance becomes smaller and smaller. If the density of the electron is high, the balance will be small. Right? And so the potential, the maximum potential disturbance is delta V0, delta V0. And the balance, for the balance lambda d is somewhere at this place. Okay, so at lambda d, the disturbance of the potential will drop to 0.7, 0.37. So this value is 1 over the exponent. Okay, so the balance is that much. So in our class, we are focus on the plasma phenomena. And when we study plasma, we just consider the collective phenomena. Okay. So if the scale is large enough, we can consider the electrons and ions in plasma are free. So they move freely, okay. And with such a large scale, the collective phenomena of plasma can be described. So the first one here is the plasma shift. The second one is bipolar diffusion, and the third one is the oscillation of plasma. So this is the analysis of the first collective phenomena, plasma shift. Okay. So in these two figures, this is at the beginning, at initial. If there is a plasma, right? Plasma with very, very large size, very, very large volume, okay? So we can consider inside the plasma, the potential is equal all over the place. So plasma is equipotential, okay? Inside the plasma. Plasma potential is equal all over the system. Okay, and then we can place two pieces of metal as a chamber wall, just like stainless steel. So at the beginning, there was a uniform plasma, and then you can insert two pieces of metal, and the metal plates are grounded. So it means the surface of metal plate has 0 volt. The potential is 0 volt. Okay. So this is at the beginning condition. And the plasma, we have already known the plasma is quasi-neutral, right? Quasi-neutral means the number of electrons and number of the positive ions are equal if the positive ion is monovalence. Okay, so the negative charge and positive charges are equal. The number of negative charge or the density of electrons and density of ions are equal. Okay, so in this upper left figure, the vertical axis shows the density of charged particle. So inside the plasma at the beginning, the electron density and ion density are equal, right? And since the metal plates are grounded, so the potential equals to 0 volt. And if the potential is uniform, right? Okay, so if we divide it by the delta V or delta phi here is the potential, or over delta X, delta phi over delta X or delta V over delta X still equals to 0. So it means there is no electrical field inside plasma at the beginning. Okay. But later on, after you place to a metal plate in the plasma system for a while, you can see the potential distribution of plasma change. And the electron density distribution and ion density distribution also change. Their profile change. Okay. The reason is the difference of the traveling velocity of ions and electrons. So inside the plasma, the ions and electrons can travel freely, right? But the velocity of ions and the velocity of electrons can be estimated. Okay. So the velocity of electron, right, equals to a square root of the charge of electron times the T. T is the electron temperature divided by M. M is the mass of electron. And the velocity of ions, right, equals to the charge, right, times the ion temperature divided by the mass of ion. So from these two, if we compare these two terms, we can find out that velocity of electron, thermal velocity of electron is at least 100 times larger than the thermal velocity of ion. So in other words, the electrons travel at much faster velocity than the ions in the plasma, in the plasma, and they can travel at random directions. But if we insert two pieces of metal plate here, right, and then we can look at the surface of the plate. So the surface will be bombarded by electrons and ions. And if we only consider the direction normal to the surface, of the metal plate, so electron and the ions, when they come to the surface of the plate, the velocity of electron is much higher than the velocity of ions, so that we can calculate the flux of electron and the flux of ions along this direction. So the flux of electrons is proportional to the density of electron times velocity of electron. This is the electron flux. And the ion flux is proportional to the density of ion times velocity of ion. Right. And since the density of electron and density of ions are equal in a quasi-neutral plasma, so the flux, right, will only depend on the velocity. And the velocity of electron is at least 100 times the velocity of ion. So it means if we just look at this surface, the metal plate surface, the metal plate will collect much more electrons than the ions within a certain time period. Okay. So once these charged particles collide with a piece of metal and the metal is grounded, and we can find out the charge will lose. electrons will lose to the metal plate. And when the cation collide with the surface of the metal plate, the cation will lose the positive charge. Lost positive charge. And the cation will become neutral atoms and reflect back to the plasma. Okay? So with a fixed period of time, and we can find out in this place near the surface of the metal plate, right? Both electrons and ions, right, lost their charge to the metal plate. But since the velocity of electron is much higher than the velocity of ion, so that the electron flux, the loss of the electron is much higher than the loss of ion. So in this region, we can find out the density of electron become smaller than the density of ion in this region. Okay, so the result is the n sub I is greater than the n sub E. So in this region, there are more positive charge than negative charge. And this region has a positive space charge. Positive space charge, okay. Okay, so the density distribution look like this way. So inside the plasma, the density of ion and density of electrons are still equal, right? The same. But near this space, the density of ion is larger than the density of electron. So this part has extra positive charge. So we can say in this region has positive space charge. Okay. So if we look at the potential distribution, we can find out if this state is steady. If this state is steady, okay, and then there will be a electrical field built up in the positive space charge region. There will be an electrical field built up. So such electrical field will pull the electron back. So actually will decelerate the electron, such electrical field, and accelerate ions, right, in this region. And the potential will look like this way. So at the center of the plasma, the potential become positive compared to the ground. At the ground, the potential is 0 volt. 0 volt, okay? And since there are more positive charge, right, in this region, so in the total plasma becomes slightly positive charge. So the plasma is not real neutral. The plasma is quasi-neutral. So the plasma state has a little bit larger ion density than electron density. So the plasma is positive charge. So the potential will look like this way. And the potential difference between the plasma and the ground electron, the ground metal plate, equals to Vp. P is plasma. So this potential is named plasma potential. Okay. So if we look at this space far away from the metal plate, the plasma potential is still uniform. And if we divide it by the delta V by delta X inside this region, we got the electrical field, right? But the electrical field will be 0 inside this region. but the electrical field near the metal plate, right, is not zero, okay, because of the positive space charge. So we can draw the electrical field, the direction of electrical field. In this region, the E field point, right, from plasma to surface of metal plate. And in this region, the electrical field. Okay, actually, in this figure have already draw the label the electrical field, direction of electrical field. Right. Okay. So, so this region has different properties compared to the inner part of the plasma, and this region is named sheath, ground sheath. Ground sheath. If the metal plates are grounded, there will be a ground sheath generated between surface of metal and the main volume of plasma. And the sheath is very important because later on when we place a material inside plasma, the materials does not contact the inner part of plasma, but instead there will be a sheath forms between the materials and plasma. So there are different sheaths, and this is the first kind of sheath, which is called ground sheath. Okay, and sometimes we use S to represent the sheath region. Okay. Okay. Any question about the sheath, the ground sheath? This is the first sheath. Okay. So the length of sheath usually is typically several divided lengths in thickness, or the thickness of the sheath. Okay. Okay. And the second plasma sheath is the floating sheath. Okay. So in the first sheath, the slide of this first sheath, we place metal plate, and the metal plate is grounded. So the sheath formed between the metal plate and the plasma, main volume of plasma, is named ground sheath. Ground sheath. Okay. And the second sheath is the floating sheath. Floating sheath. Okay. So in this case, we place a piece of substrate or a piece of materials inside the plasma. Okay. So for example, if we place a piece of plastic, right? Plastic is an insulator. Plastic is an insulator. So if we place a plastic inside the plasma, so again, the surface of plastic will be collided by electrons and ions. Electrons and ions, right? And at the beginning, the plasma is uniform, right? So that density of electrons and ions are equal inside the plasma. But the velocity of electrons are much larger than the velocity of ions. So again, if we look at the surface of the plastic substrate, the surface is collided by electrons and ions, and then we can calculate the flux of electron and the flux of ion. The flux, right? So at the beginning, the flux of electron is larger than the flux of ions. So within a certain period of time, the plasma will lose more electrons than the ions, more electrons. And those electrons and ions, when they collide with the insulator, they lost their charge to the insulator. But no, the insulator is not grounded. Even you ground the insulator, the charge cannot be conducted away. So the charges will accumulate on the surface of insulator. And since at the beginning they are, for a certain period of time, the electron flux is larger than the ion flux. So the surface collects more negative charge than positive charge. So in other words, the surface of the plastic will be charged negatively. So there are charges build up, negative charge build up on the surface. Okay. So the surface there will be a negative charge. So again, if we look at the potential of the system, right, and the surface of the plastic has the negative charge compared to the plasma, okay. So the potential in the system, the potential distribution of the system will change to this way. So left part is the main volume or main body of plasma, right? And this part is the plastic surface. And plastic surface is negatively charged, so that the potential at the surface of plasma become negative, okay? So the potential of plasma is positive, and the potential of this insulator surface or plastic surface become negative, even though the plastic is not grounded, okay? So there's a potential difference between plastic and plasma. And this potential difference is named floating potential. And sometimes we use the Vp minus or subtract the Vf as the floating potential. And sometimes people just use Vf to represent floating potential, okay? So the floating potential actually is the potential between plasma and the surface of a material. If it's an insulator, if you insert the insulator inside the plasma, okay? And if you insert a piece of metal inside the plasma, right, and let it float, it means that the metal plate does not connect it ground wire. And again, the metal plate will also collect charges and become negatively charged. So the metal plate will also experience this kind of condition and build up a negative charge and behave a negative potential compared with the plasma potential. Okay, and this kind of condition is called floating condition. So it's either an isolated conductor surface or insulating material. When they contact plasma, they will build up a floating potential like this way. Okay, and the floating potential can be estimated by this equation. Okay, so it depends on electron temperature and the mass of electron and mass of ion. Okay, and for argon plasma, the floating potential is around 5 times KTE. K is Boltzmann constant. Okay. So if the electron temperature is around 6 eV, and then the floating potential of argon will be around minus 30 volts or minus 40 volts. Okay, and this potential is relative to the plasma potential. So this value is Vp minus Vf. Okay. So these two slides shows how the sheath was built up. How the sheath was built up, or maybe we should look at this figure. Okay. So once the sheath is built up like this way, there will be an electrical field in the sheath region. Right? There is no electrical field in the plasma volume, but there is an electrical field in the sheath region. So when the positive ion or cation travel across the dashed line, and when these positive ions enter the floating sheath region, the positive ion can be accelerated by electrical field. So it means the velocity of positive ions become larger, accelerated by electrical field. And when electrons travel across this dashed line, when they enter the floating sheath region, the electrical field decelerate the electron. So it means the velocity of electrons will become smaller. Okay. So at the beginning, right, on the surface of this insulator, we can find out the flux of electrons is much larger than the flux of ion. But after the sheath is built up, and the plasma reach a steady condition. So in the sheath region, we can find out the flux of electron and flux of ions become equal in a steady state. Flux of electron and flux of ions becomes equal. So that the surface of the insulator will not charge up more. They will just reach a steady condition, negative charge, but the number of charge will remain the same. So they will reach a steady condition. So in this steady condition, for a certain period of time, the surface of the insulator collect the same amount of electrons and ions. same amount of electrons and ions at a steady state. So after they build up this potential distribution. Okay. So the same thing happens in the ground sheath. In ground sheath. Okay. So in ground sheath, you also reach a steady state. Okay. Steady state. Then in a ground sheath. So in a steady state, the flux, right, of electron and flux ion to the surface of the ground metal plate are equal. But at the beginning, the flux of electrons is much larger than the flux of ion. Okay. So this figure shows that after the sheath is formed, the electrons will be repelled, and the ions will not repelled but decelerated, and ions will be accelerated. So this figure shows for electrons that when they come to the sheath region, they lost their energy, start losing their energy. So they need, so it's difficult to travel to the surface of the insulator. And for ions, they gain energy, so they are accelerated, and then they can easily reach the surface of the insulator, and eventually the electron flux and ion flux are equal. So in Chapman's book, C sub E means the velocity of electron, and here is the velocity of ion. So after the system reaches a steady state, right, the flux of electron and flux of ions are equal. Okay.